My friend asked me to show off some of the things that I've been doing with my FPGA board, so I will try to do that with this video. There may be some problems. You can see that the LED is getting blown out on my camera here, but we'll do the best we can. Anyway, so this is my FPGA board. It's a little $100 board from TerraSic, whatever their name is. And actually I like it a lot. It's pretty simple. It's got lots of IOs. It's got very few onboard things. It's got a nice chunk of RAM on the back. I haven't gotten a chance to play with that yet, but in any case, so the simple circuit that I've made so far is this. I've got some dip switches down here and I can flip them, and as I flip them, if I can get at them, you can see that LEDs turn on. So there are a couple LEDs. And you can turn on up to 4. There are 8 LEDs. These are the low 4. And then these control them directly. Then, if you come around here and hit one of these push buttons up here, what happens is the current dialed-in number will get added to the accumulator, which starts at 0. And you can see every time I hit this button, the accumulator gets incremented by 1, because that's what the dip switches currently say. And I can flip that to a different number. And you can see that what's being shown here is actually the sort of like live preview. If I flip them all down, that's what's currently in the accumulator. And then this is what will be in the accumulator if you hit that button. Alright, so I can add larger numbers at a time. And of course with this other button I can reset it. Well, and it would make more sense if these were all flipped down when I reset it. So there you go, I can reset it. I guess I can add 0 as well, I never tried that, but hooray. Anyway, so the interesting thing here is not the accumulator or the adder. Those are really simple. Actually, the debouncing logic for those switches was interesting. The switches are connected using a Schmitt trigger, and that helps a bit, but I found just practically it, maybe because of the tininess of the switch or the way that I'm activating it, I found that the trigger wasn't good enough, so I had to actually write some debouncing circuitry. And I learned a lot about Verilog in doing that, so maybe I'll get to that. Okay, like I threatened, I'm going to show you the Verilog for my switch debounce. Actually, this is an older version of the switch debounce, and I want to kind of show off one of the interesting things about Verilog, or at least with Altera's tools. So this is the original version, and there were some nice things about this. I have a state machine. So basically, the idea is that there are four states. There's sort of the baseline default state where you haven't pushed it and nothing's going on. When you press the button down, then you move to the second state, which is you have pressed the button, and that actually starts a timer, or at least a counter. And while that counter is going, you can't transition out of that state. You will remain in that state. Once the counter gets to the end, then you kind of move to the third state, which is where it's ready to sort of process the button up event. And then after the third state, you'll transition to the fourth state where it runs the counter again. The idea basically being to make it so that you have dead zone after either the button pushes down or the button releases. There will be dead space where no transitions can occur. And then once that counter has elapsed, then the transitions can occur again. In fact, it'll sample the current state of that. So anyway, it's relatively simple, but it works fairly well. So right, this has the state is explicit here as state, and you can see the 4 states here. One of the downsides to this is that I sort of have this priority logic where the state is sort of like the highest priority, and then there are also these if statements inside of a couple of the cases. And we can actually look at the viewer, which is this, and you can see that it in fact generated a state machine. And we can go into the state machine and we can see, look at that, nice transitions. So this is one of the things that the Altera toolchain apparently does, is detect state machines in your code and give you this nice, you can actually apparently edit them in here, although I haven't tried that. But anyway, so this is that logic, and it's nice. If we look at the compilation report, you'll see some stats. You'll see that we're using 22 logic elements to generate this, which is kind of higher than I expected, but I don't really have a good sense of these things yet. Anyway, now I'll show you the other design that I came up with. So this is the module as it currently stands. The big difference from before is that I've combined the isMax, which was the condition that was inside of the cases before, with the explicit state, and turned that into a big case X expression. And you can see that I've got some do not cares here, down here. But this is essentially a mechanical transform of what I had before. Now if we look at it in the viewer, you can see that it has essentially destroyed the state machine. And you can't see the nice state machine block anymore. You can't go into the state machine viewer. I don't know how much of a loss that really is. It seemed like it would be cool, but whatever. But yeah, I mean, like for example, this is the register that stores the state, in which you didn't see in the previous diagram. Now, one of the nice things about this, though, is despite the fact that we destroyed the state machine, we're using 5 logic elements less than before, which was surprising. I suspect that has more to do with the fact that my logic is now flatter. It's not chained as deeply anymore, which means that it should be faster, and the fact that it takes up less space on the FPGA is pretty nice too. So that's that. I intend to continue to do some more stuff with this, hopefully over the holidays, and see what I come up with.